Let's go over gas chromatography. This is a method that separates the components of a mixture for analysis. It gives us helpful information about the number and relative abundance of those components. So here's how it works. If you have a mixture of multiple compounds, it could be very few or many, gas chromatography will help us separate them and see how many there are, as well as the relative ratio of those compounds. Let's use a relatively simple example where we have a mixture of 3 compounds. The 3 compounds have different physical properties, including boiling point. So there's 3 different colors of circles meant to indicate 3 different kinds of compounds. Now here is a characterization of a gas chromatograph. There's an injection port where you insert the sample, and then the molecules in the sample, travel through a column and end up at a detector. Now, if you see injection port, you might be thinking about a syringe, and you would be right. What happens is you use a small syringe to draw up some sample, it's usually in the liquid phase, and put it through the injection port, which is very hot, which vaporizes the sample. So all of the molecules go into the gas phase. The gas chromatograph has a carrier gas, in this case helium, that moves those injected molecules through this column. And the column is very, very long, 40 meters or so. And as those molecules travel through the column, they separate based on physical properties. And one of the most notorious physical properties is boiling point. So as those molecules that are different from one another travel through the column, they separate into bands of like molecules. Now the gray balls have the lowest boiling point, and lower boiling compounds travel fastest through the column. Those compounds that have higher boiling points, like the clear circles, well, they travel slower and spend a longer time in the column. But the carrier gas moves all of the molecules eventually through the column where they hit the detector. Now the detector generates what we call a chromatogram, and from that, we can determine the number of components that were in the mixture and quantify the relative abundance. So let's take a look at what that chromatogram and the output looks like. Again, here's a schematic of this example where we have our lower boiling compound traveling faster through the column and reaching the detector first. Well, here's a chromatogram. The x-axis is the retention time, and its unit is usually minutes. The y-axis is some measure of abundance or intensity of that signal. This chromatogram has 3 peaks or signals, A, B, and C. A has the lowest retention time, which means that A corresponds to the compound with the lowest boiling point because it traveled fastest through the column. That's the gray circle for this example. Now B had the middle boiling point, and so it spent the next lowest time in the column. That's the black circle. And the compound with the highest boiling point spent the most time in the column, taking the longest to travel through it. That's the peak marked C, corresponding to the clear circles. We have some GC chromatographs in the back of the organic lab along the line of benches that faces the window. So there's an oven inside the box, and there's a little port right here. That's how we're going to inject sample. But I think it's helpful to look inside. So we inject here, and then inside there, your sample goes through this spot, which vaporizes any liquid. Then the gas or vapor goes through this long coil, copper coil. It's like a tube. It's at least 40 meters. Then, over time, the molecules separate by boiling point. The higher boiling molecules take longer to get through the tube, and the lower boiling molecules speed through more quickly. And they come at the end, and they go through what we call a detector. And so what you see as your sample runs on the computer screen is, as no compound is coming out the detector, we have a flat line. Then as a little compound comes out, we have a little spike. The more compound there is, the higher the spike. All right, so this is time on the x-axis, or retention time, and the y-axis is essentially intensity. Rough and tough, the lower boiling things come out first, That's these guys, medium boiling point, highest boiling point. So we can see that we have a major product in this sample by far, this high spike, but the instrument will integrate or measure the area underneath the signal to help us quantify that and get us percent purity. So when I go file, print, it's going to print a nice report right in the lab. It'll tell me the x-axis values of those signals along with the integration or the relative percent area of them. This is a printout of the actual chromatogram, and here at the bottom is a table, my signals and the percent area. So for this student, the largest signal at 4.550 minutes is 95.5% of the total material, 95.5% pure. Alright, so let's take a look at how to inject the sample. We're going to use a 10 microliter syringe. It's glass with a very thin needle. Okay, so the first step is to clean the syringe, and so we use acetone, which is a common organic solvent. It takes nail polish off, actually. Alright, so what you dip this in, you pull the plunger up, and you just expel it. You can do this in a hood if you're in the lab. Just as like one little drop, so it's fine to do that. One rinse, maybe a second rinse. You want to be gentle with the plunger. Okay, then the next step would be to rinse it with your sample, because acetone is a compound, we want to get rid of it. So we put the syringe needle in, we draw up the sample, and expel it. Okay. Then, this is a 10 microliter syringe. We want 0.5 microliters. Not 5, which is halfway, but 0.5. So you dip it in, and gently draw up just a little bit, half a microliter. Alright, so then once your syringe is loaded, then it's time to inject the sample. What we want to do is take the needle, put it right through this little hole, like a bullseye, and come at it from the front. The needle needs to go all the way in until it's touching, okay? Before you depress the plunger. If you felt resistance, you can just back it out and try again. Alright, okay, then, once it's in, depress the plunger, then you reach over and press spacebar to get the run going. So it runs, and then once no more peaks or signals are coming, it flatlines, we stop the run.